Are you in my layer? Said the router. In this nugget, we're going to focus on which common network components, like switches and routers, fit very clearly into which layers of the OSI reference model. It'll be a great review of some of the concepts, plus an opportunity to dig even deeper and make sure we're solid on the fundamentals of our networking. Let's jump in. So in a previous nugget, we took a look at the OSI reference model, and now I'd like to take a moment and review a couple of the basics with you, and then introduce some new concepts as well. First and foremost, I'd like to ask you, do you remember the names of the OSI reference model layers? So layer 1 right here, what was it called? You remember? It's at the very bottom, responsible for bits and the transmission of those bits across the network. Very good. It's the physical layer. And how about layer 2 of the OSI reference model? What is it called? Do you remember? If you do, go ahead and tell me, what is it? Layer 2, data link layer. And if we go back to our analogy, the data link layer is responsible for envelope stuffing, which means putting the data in the right frame, and also making sure that we add the layer 2 addresses, the source address and the destination address, to each of those PDUs, those frames, at layer 2. And at layer 3, what was the name of that layer? You remember? This is the layer where we deal with logical IP addressing or logical addressing, and this is the network layer. All right. So fabulous. That's a little bit of a review. Now what I'd like to do is take a look at the big picture here and talk about why we have a network in the first place. Without a network, it's pretty much a lonely place. We don't have anything to do except communicate with our own computer, its own hard drive, and the resources that are directly attached. But see, if we have a network, we could have a printer right here, and we could share that printer. So user 1 and user 2 could both share that printer. In fact, a user out of a branch office here in Des Moines, Iowa, at his PC right here, if we had a network in place, this user here, if he needed to print a report, he could print it to this printer way over here. And so the benefit of sharing resources is huge as we take a look at computer networks. So I'd like to focus on just a couple of the basic components that we're going to find at each of the layers of the OSI reference model. And we'll start off with layer 1 here. First and foremost, to get on the network, you need to have not only the logic inside the computer, protocol stack, but you also need to have a network interface card, and most computers are going to have a network interface card built in. So sometimes we'll call it a NIC for short, network interface card. So this laptop has a built-in NIC, and this printer has a built-in NIC, this server has a built-in NIC, and so does that one, and this router right here has a built-in NIC, and the switch has ports that we can connect into as well. And these routers on the internet, everybody's got a network interface card. And you know what the network interface card gives you? It gives you an interface or a way to connect to the network. So let's take a close look at what a network interface card looks like close up. So here's a close-up of a network interface card, and this one actually has a little RJ45 jack right there, and that's just a fancy way of saying register jack RJ45 is a type of connector. So if everybody uses the same types of connectors for their cables as they plug in, we're going to have some compatibility, and that's a beautiful thing. So on this PC, on this laptop, on this printer, they've all got usually a built-in from the factory network interface card, and this one here is one that you can add to a computer if for some crazy reason in the 21st century it didn't have a network card and our network interface card already built into it. So the network interface card is the interface, if you will, the way to get to the physical network from a computer's perspective, and that's why definitely the physical components on a network interface card are part of the physical layer of the OSI reference model. So once we have the network interface card and we want to connect to the network, we're next going to use this cable right here. And this cable is represented by this cable right here. So you'll notice this cable has RJ45 connectors as well. So this is an RJ45 socket, and this is an RJ45 connector on the cable. We take that end of the cable, plug it into that. We take the other end of the cable and physically plug it into this device here called a switch, which we'll talk about in a moment. And that's how we get physical access from this computer to the network. Now, some devices don't even need a cable. We might use wireless. And so you could have a laptop or a PC out here, and it's got a built-in wireless card, and there won't be any physical cables whatsoever between that PC and the network. But we're still talking about the physical layer because we're sending bits, even though they're across the airwaves and you can't physically touch the air as a tangible item. The airwaves also are part of the physical layer as we talk about moving bits across. So at layer 1 of the OSI reference model, we have network interface cards. We have cables and connectors that allow the physical connectivity to the network. And we have another device called a hub. Now, what exactly is a hub? So here is a hub. A hub is simply a device, and this is an 8-port hub, so it has these RJ45 sockets. And the cool thing about using RJ45 in very many places is that if you have RJ45 cables, they fit perfectly into an RJ45 socket. So let's say we have 3 PCs, PC1, PC2, and PC3. And I don't know why PC2 got an extra C in there, but that's okay. So we have these 3 PCs, and we want to share and do networking between those devices. Now, if we're not using wireless, we need some physical connectivity, and what we can use is we can use the hub. We'll simply take a cable that has the RJ45 connector on the network interface card end and plug it into here. So the cable would have an RJ45 connector at both ends. We plug PC2 into maybe port 6 and plug PC3 into port 3. It really doesn't matter. They're just numbered, and then we could pick any port we wanted to. You know, any port in a storm, that kind of stuff. So what happens now when these computers are all now physically connected at the physical layer using a hub? Well, now if PC1 sends data bits into the hub, what the hub's going to do is the hub says, oh, I'm a layer 1 device. My job is to repeat. In fact, every time you see the word hub, I want you to think repeater. Repeater of bits. I need a spell check. Repeater of bits. That'll work. So he repeats bits for a living. That's what he does. What do you mean, Keith, repeats bits? Well, if PC1 is sending bits into the hub is going to say, oh, I need to repeat those bits, and it will repeat them out all the other ports. So as those ports come out here, they'll be sent. That's all it's doing. So it simply takes bits in on one port, and it'll send it out to all the other active ports. Well, what if PC3 sends bits into the hub? Well, the hub receives those bits here on port 3 and would send them out on port 6 and also out on port 8. And that's all a hub does for a living. In fact, a hub is considered a layer 1 device because it has no knowledge that those bits it's forwarding have any other meaning at layer 2 as we look at frames or as packets at layer 3. It only understands bits, and it's just check. Repeater of bits. That'll work. So he repeats bits for a living. That's what he does. What do you mean Keith repeats bits? Well, PC1 is sending bits into the hub is going to say, oh, I need to repeat those bits, and it will repeat them out all the other ports. So as those ports come out here, they'll be sent. That's all it's doing. So it simply takes bits in on one port, and it'll send it out to all the other active ports. Well, what if PC3 sends bits into the hub? Well, the hub receives those bits here on port 3 and would send them out on port 6 and also out on port 8. And that's all a hub does for a living. In fact, a hub is considered a layer 1 device because it has no knowledge that those bits it's forwarding have any other meaning at layer 2 as we look at frames or as packets at layer 3. It only understands bits, and its job in life is to repeat. So that's it for layer 1. Quick review. We have network interface cards that let our devices, for example, our routers and our computers, connect into the network. We have cables and connections to like RJ45 connectors to allow those connections to happen. The hub, as we just took a look at, is simply a repeater. It's like a physical way to connect several devices together. Also, I want to point out that we don't use hubs very much anymore. It's mostly for historical purposes because we have something much, much better than a hub coming up here in just a moment. I'll show you. And we also are dealing with bits, which is the PDU at layer 1 of the OSI reference model. So let's move up the protocol stack and let's take a look at the common elements that we would find at layer 2. At layer 2 of the OSI model, we have the data link layer. And what was our little analogy? We used the envelope guy. Envelope. Now, at layer 2, we're taking the data that we receive from layer 3 as we encapsulate and go down the protocol stack. We put it in the correct envelope, which is another way of saying the correct frame, and we also add some header information. Remember what we add? Let's take a look at what we add as a reminder of what layer 2 is doing for a living. So here's the protocol analyzer that we used in a previous nugget as we were investigating and learning about the OSI reference model. And we also identified that this is layer 5 and this is layer 4 and 3 and 2 and 1. If we open up the layer 2 header again, that's the information added by the layer 2 function logically in the OSI reference model, we're going to see that the major components added were the source and destination layer 2 addresses. And so here's the unique MAC address that's assigned to my PC, and here's the unique MAC address that's assigned to the router that I'm using to forward traffic off of this network. So this is my PC here, and my router has, I'll put lines there. So this is my source, and my destination is right there. Why? Because my PC needed to forward a frame to the router so the router could take my packet, which was addressed to google.com, and make a forwarding decision in that general direction. So that's the ball game that we're playing. Move the packet towards its destination, and if everybody cooperates, eventually that packet will make it. So this MAC address right here, how would we see what the MAC address is on your computer or my computer? And the answer to that is pretty simple. We would just go ahead and ask the computer to tell us. So if we bring in the computer, and this is something you can do absolutely right along with me, what we're going to do is we're going to go to this is Windows XP, and on Windows 7 it's generally the same. If you go to a command prompt on the operating system that you're running, Windows anything, the way you'd verify what your MAC address is by using this command, ipconfig /all. I'd like you to go ahead and try that. So go ahead and pause this, and once you've done ipconfig /all from a command prompt, come back and we'll take a look at the results. Now, if you're on a Macintosh or if you're on Linux, it's going to be ifconfig. So swap out the P with an F, and you don't have to do /all, just ifconfig on Mac or Linux, and you'll get a very similar result. Okay, so ipconfig /all, I just ran that, and I've got several network interface cards and several things running at the same time. But here's what I want to point out. This is my primary network interface card right here. It's showing me that it's got an IP address and some other fancy bells and whistles. But here's the piece I want you to focus on with me. Check this out. This is showing me that I have a physical address. See it right there? The physical address. And what that really means is this is the MAC address. So we could say that a physical address, a MAC address, media access control address, a layer 2 address, we're all talking about the same exact thing on my little Ethernet network here. And it shows me that this is the actual MAC address being used. So remember we had the analogy of the mailbox on my street, and everybody had their slot numbers, like, you know, somebody has slot 1 and somebody has slot 2 and somebody has slot 3. Well, inside of a computer network, this network card on PC1 has a MAC address. It happens to be this one right here. And this PC is going to have a different layer 2 MAC address, and the printer is going to have also yet a different layer 2 MAC address. Now, how do we make sure those are all unique? How does that, what's the magic in that? Here's the magic. If you and I want to go into business of manufacturing network cards for this type of network, which is an Ethernet network, we'll talk about the standards and how that all works. But for now, let's say we want to manufacture Ethernet network interface cards. You and I, we're going in business. Well, how do we start? Well, we get some money, we get some venture capitalists, we get some manufacturing people involved, and we start building cards. But what we're also going to do is we're going to have to go and be assigned what's called a organizational unique identifier, an OUI. And this OUI is going to be 6 characters long. See, this one right here, 001B77, that was assigned to Intel. And companies like Intel and Cisco, they've got tons and tons and tons of OUIs assigned to them. But here's how it works. So you and I go into business. We apply for our own individual organizational unique identifier. And let's say we get 3, 4, 5, 6, 7, 8. That's the first 6 digits that they give us. You'll notice this is 12 digits long. So now as we make our cards, we could use these first 6 digits for the first 6 digits of all of our cards, and then the first card we make is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let me back that off one step. There we go. 1, 2, 3. So our first card is 34, 56, 78, 000001. And the next card is 000002. And then 000003. 000004. And we could make a whole bunch of cards using just those first 6 characters. So that's behind the scenes how we know that all of the cards are unique, because every manufacturer is assigned the first 6 digits, which is unique to that manufacturer, and then that manufacturer keeps track of all the last 6 digits and makes sure they're all unique. So this MAC address right here is 001B77123456. It's a lot longer than a slot number on a mailbox, but effectively it's the same thing. That's how we know where our neighbors are. We can forward data directly in frames at layer 2 to the MAC address of the device that we want to talk to. So in this exercise, I hope that you've taken a moment and identified what your layer 2 MAC address is as well. And if we go back to our protocol analyzer that captured the packets from our earlier session, it's also going to confirm for us that there is my layer 2 address, my MAC address, and it's been inserted inside the layer 2 header, which is now we can call a frame, that all that data. And if you take a look at also my protocol analyzer said, oh, this is a MAC address assigned to Intel Corporation. And it knew that because the first 6 characters it knew in my protocol analyzer that that was associated with Intel. If your protocol analyzer doesn't recognize or understand or doesn't know what the first 6 digits represent as far as the vendor, it'll just leave them as showing you, and it won't list the actual company name right here for the first 6 characters. All right, so we've taken a look at layer 2, the MAC address, which is right here. The network interface card, this is interesting. Because the network interface card itself has this burned in layer 2 address, the network interface card could also be considered a layer 2 device because it has that layer 2 address. So it fits in at layer 1 from a physical perspective. It also fits in from a layer 2 perspective in the fact that it does absolutely deal with and work with that layer 2 physical addresses burned in. So what are these next items here? Well, a switch and a bridge. What in the world are those? Well, I happen to have one right here in our network topology, and this, my friends, is a switch. Now, I gave you 2 different views of it. I thought you'd like to see both. This is the icon that we'll normally see in a network diagram that represents a switch, and this is the image of a physical switch. And you'll notice it has ports. These are RJ45 jacks or sockets, if you will. And I'll put that in RJ45. And so if you look at it, you think, well, Keith, it looks a lot like a hub. You take the network interface card, connects to a cable, goes into this port, just like on a hub. But let me tell you a little story about what a switch is going to do for a living. A switch has an attitude. It doesn't like to forward traffic out every single port. Let's walk through that, what a switch does right now. So let's say we have a switch and we want to connect those same 3 devices together that we did earlier. So on this switch, it happens to be a Catalyst 3560 switch. It's got 12 ports, hence the 12. And the PoE stands for the fact that it can actually deliver power over these Ethernet ports. They have a web camera or an IP phone or something, it can actually power it. That's what that stands for. So let's say we take these 3 devices, PC 1, 2, and 3, and we plug them in. So we'll put this one into port 1, we'll put this guy into port 5, and we'll put him into port 11. And these will be RJ45 connectors here, here, and here, and also RJ45 connectors as they connect to the network interface card. And the cable will simply be what's called a patch cable. It allows you to patch in, for example, to a switch. Now, how is this different, Keith, than the hub that you described earlier? Well, the switch doesn't like to forward everything everywhere unless he has to. So the switch is considered a layer 2 device because it understands frames. Specifically, it understands the format of frames, and it also understands layer 2 addresses. And here's what it will do. So you and I know that a MAC address is 12 digits long, and that's pretty long. So let's for here, just as an example, let's just say that this device, PC1's MAC address, is AA. And I realize there's 10 more digits that need to go there, but let's just do that for short. And the PC2, its MAC address is BB. And PC3, any guesses? You got it. We'll make him CC. So those are the MAC addresses, just for pretend for a moment, for each of those devices. Now, whenever a device sends a frame into the network, what the switch is going to do, it's going to look at source MAC address. And it's going to memorize where that device lives. So if this PC sends a frame in, the switch looks at the MAC address of the source MAC address and says, oh, golly, I know that on port number 1, I'll do it right here. So port number 1, I know that the MAC address of AA lives there. And when PC2 sends its first frame into the network, the switch will say, oh my goodness, the source address of BB, I saw that incoming on port 5. It will know that port number 5, that the device with the MAC address of BB lives off that port. And as PC3 sends a frame into the network on port 11, the switch will see, oh, the source address is CC. So now, in fact, after each device sends one frame, which is going to happen almost immediately when a PC is powered up and it has a network adapter, the switch is going to know exactly where each MAC address lives. Now, that's where the magic of a layer 2 device comes into play. A layer 2 switch does selective forwarding. So now if this PC right here, PC1, forwards a frame to PC3, the switch, as that frame comes in, the switch says, oh, I know where the destination address of CC lives, and the switch will forward the packet, and I'll do this right here, and it's a little dotted, it'll forward the packet on the back plane of the switch directly to port 11 so that the PC3 can get it. And PC2 never had to see any of those bits. It never had to decide, oh, is this for me? Is it important? Is this destined for my MAC address? None of those questions came up for PC2 because the switch selectively forwarded the frame to the correct port where that MAC address lived. So the two things about a switch are this. Number one, it memorizes source MAC addresses and associates them with ports. They call it a MAC address table that the switch keeps track of. And then if the switch knows when a new frame comes into the network, if it knows where that destination is, it will only forward the frame to the port where it knows that destination MAC address is. Now, the next logical question that often comes up is, but Keith, what if there's a frame that comes into the network? Let's say PC2 sends a frame in, and the switch doesn't know. It looks at the destination MAC address, and it doesn't know where that destination lives. What does it do? In the case where the switch doesn't know where that destination MAC address is, which port it's associated with, the switch will act like a hub. And it will err on the side of caution, and it'll say, you know what, I'm not sure where this is supposed to go. I'll just forward it to every other port. So it forwarded it to both other ports that are currently active, so that whoever this frame is destined to, hopefully they would go ahead and get it. They call that an unknown. An unknown destination from the switch's perspective is going to be forwarded to all other active ports on that same switch. All right, so that's layer 2. We took a look at MAC addresses on a PC. We also identified that a network interface card could be considered a layer 2 layer 2 device because it is dealing with the layer 2 address and has that MAC address burned into it. A switch memorizes where devices live, and what the heck is a bridge? A bridge is an old name for a switch. They work virtually identical. A long time ago, when networks were first being developed, we used hubs. And then to help reduce the overhead, we moved to bridges, which would maybe take, 50 users over here and 50 users over here, and we put a bridge in between them. But really a bridge is nothing more than a switch. It forwards only based on MAC addresses where it needs to go. So a bridge in the old days might be 2 ports or 4 ports. It was fairly slow by today's standards. And a switch has multiple ports. This guy has 12. Having 48 ports or even more on a single blade is very common. So switches have lots more ports. They forward much, much faster, but the logic is the same between a switch and a bridge. And at layer 2, we're dealing with the PDU of frames. And again, a frame is nothing more than layer 3 information, the packet being handed down to layer 2, where layer 2 adds its header, which includes the source and destination MAC addresses. Now you know. Let's take our next little jaunt over to layer 3 and take a look at the common items that fit into the category of layer 3 of the OSI model. In our analogy with layer 3, it was the mailroom. And I'd like you to remember that as far as the mailroom goes, what their primary job was inside the mailroom. At layer 3 of the OSI reference model, we have the network layer. We know that. That's good. So what did the mailroom do? It added information in the header of the IP packet. The primary thing that it's adding is IP addresses. So here's what I want you to remember at this point about IP addresses. An IP address is a logical address, but really it just means that we're talking about a street and house. Like a street name and a house number, just like the ones you live on right now. So the place where you live, it's on a street with other people who have that same street name, and your house number has a unique house number. And even further, you may have like a unit number inside that building to further delineate exactly where you live. So we take a look at this network over here. We have a street, maybe that street is called 10100. And in computer networks, we name our streets. We don't name them Elm Street and Fir Street and Sunset Boulevard. We name them numbers. So this is the 10100 street as an example. This network here is the 10500 street. On the internet, there's over 400,000 streets that are being remembered by the routers that do the internet. And maybe here at a branch office we have this street. So on each street, every house is going to have its own logical house number. So maybe this is house number 5, and this is house number 6 and house number 7, and maybe the router down here is house number 8. So an IP address, and we'll take a look in a separate module on IP addressing. But for now, I want you to know that an IP address is nothing more than a street name and a house number. So what are the common elements associated with layer 3 of the OSI reference model? Primarily, it's IP addresses. So let's take a look at a few. Let me bring in we already did a PC, but let's bring in the PC again just for fun. So on a PC, if we do a command, and if you've already done this, it's great. If not, I'd like you to do it with me and maybe even do it again, but we type in ipconfig, enter. If you're on a Linux or Windows box, it would be ifconfig. And it's going to show us our IP address. So if I take a look at this right here, this is showing me my IP address on this device right here is 10.1.0.51. And what it really means is that the 10.1.0, this is my street that I have in common with all the other devices on this network over here, and the 51 is my house number. So that's my IP address. That's how it's broken down. And again, like I said, I'll show you exactly how we divide that up in a separate nugget dedicated just to that. So that's an IP version 4 address. Well, there's another version of IP out there. It's called IP version 6. Now, why do we have that? Well, initially, when TCP/IP protocol suite was being developed, they had no idea that it was going to be so huge and be used by the internet, by virtually every individual on the planet having access to it. So over a decade ago, they started working on a new version of IP called IPv6. And instead of using short, little, easy to work with IP addresses, they started working with IP addresses like this right here. That little piece at the end is the way Windows tags it. So an IPv6 address, we'll do IPv4 for here, and this is an IP version 6. So an IPv6 address is much, much longer, and we'll talk about that also in a separate nugget on IP addressing. But really, an IPv6 address also has the same two basic components. It's got the street portion, and it's also got a house portion, just like IPv4. It's just that it's much, much longer. Now, one of the interesting things, I think, that comes up is something called the EUI64. And I'm going to introduce it here because it's part of the objectives inside of the CompTIA that I want you to be aware of right now. And the EUI64 says this. It says everybody needs to have a house number on a street. So for now, let's say that this FV80 is the street, and let's say that this is the actual house number on that street. What the EUI64 does, it says we're going to use the MAC address, which is the layer 2 address, and we're going to use that to create much of, not all of, but much of the layer 3 host address. And I'll cover that more in detail in IPv6, but for now, the EUI64 is simply a way of creating a 64-bit host ID, an IPv6 layer 3 address, based on the bits that are available from the MAC address. So that's what an EUI64 is, creating a 64-bit host ID or host address, house address, based on the MAC address that's on that computer to begin with. And again, more to come as we take a look at the details of IPv6. So let's see what else is in my objectives here. Layer 3, the IPv4 and IPv6 addresses. In fact, let me give you one more view of that. Let me bring up, this is a router. So routers, here we have, and the way the flow goes is this. PCs that want to communicate on their local networks, they can send their frames directly, no problem, because they have reachability. But if a device wants to go maybe out to the internet or beyond their local network, they're going to go ahead and send frames to their default gateway. The default gateway, hopefully, will, when he receives the frame, will de-encapsulate that, and it will say, oh my goodness, this frame is directed to me, but as it looks at layer 3, it says, oh, this packet is destined out here to maybe the 77 network, google.com. And then the router says, I know how to get there, and hopefully he'll re-encapsulate and forward the packet to the next router, which is right here. This router will receive it and say, oh, this frame at layer 2 was sent to me, so I will open it up and de-encapsulate it. But when it gets to layer 3, this router says, oh, I'm not 77, but I know how to get there. It will re-encapsulate it and send it off to its service provider or the next hop. And that's how the network operates. In fact, if we wanted to really reinforce the concepts of the Osi Reference Model, we could do it right here with a simple analogy or simple walkthrough. I say we do it. For this analogy, instead of going all the way out to the internet, let's just say that we have this PC that's going to go to our internal web server. And the web server has maybe a company web page or what have you. So let's draw our OSI reference model. And we've got the application layer on top, and we have the physical layer at the bottom, and then we have our data link, and we have our network, and we have our transport. There's 1, 2, 3, 4, and 5. All right, so when the PC wants to make a request, the user sits in front of the computer, runs an application like maybe a browser, and that browser is going to go ahead and make a request out to the server. So let's say we put in the IP address of the actual server we want to get to. So maybe this is 10.5.1.1. We're over here at 10.1.0.51 or whatever our IP address is. And let's say this part is our street. There's our street, and this is our house number, and this is the street that the server's on, and that's the house number for the server on that street, and we want to make a request. So we go through the process of saying, I would like to talk to this web server. At layer 4, it gets encapsulated. The session layer, or the application layer, assigns ports involved for that conversation. It goes down to the transport layer. Transport layer says, oh, this is HTTP request. That gets TCP services, which are reliable. That gets encapsulated into the network layer, which adds the IP addresses. So the source IP address at layer 3, we'd have the source IP address of 10.1.0.51, and the destination address would be 10.5.1.1. Are you with me? That's exactly how it works. Now the next part is, at layer 2, this PC is saying, oh my goodness, I'm on street 10.1.0. The destination is on 10.5.1. It's on a different street. So the PC says in its mind, I have to use a default gateway. I have to use the mailman to get out. And that mailman is a layer 3 device called a router. So what will happen is this PC has been trained that its default gateway is, let's say, 10.1.0.1. And so street is the same, but the house number is 1. So as he gets ready to send the data and layer 2 are about to encapsulate it, what source and destination addresses are we going to use? Well, if the PC's MAC address is AA and the router's MAC address on this network is BB, the PC, because he knows who his default gateway is, it's been configured, the PC is going to put the layer 2 address of his default gateway at layer 2, and then he's going to spit the bits out on the wire. Are you with me? So it's a set of rules that we definitely need to be familiar with, but that's exactly how it works. So now that the PC has been through its protocol stack logically, it gets to the switch. Let's take a look at what the switch does. The switch receives the bits, but it's a layer 2 device, and it doesn't like forwarding frames to everything. So it receives the bits, and it reassembles those, if you will, or takes a look at the frames of data, and it looks at the destination MAC address. So we could say the switch is looking at the data all the way up through layer 2 of the Osi Reference Model. So the switch sees it, looks at the destination MAC address, makes a forwarding decision, and forwards it only to the port where the router is. So now the router gets it. And the bits are there, so he receives the bits at layer 1. He looks at the layer 2 information, and by George, it's destined to the destination address of BB. So it's like having a book that you're interested in. So you're reading a book, and you say, wow, I'm going to keep reading. Because the layer 2 address is addressed to this router, he continues to de-encapsulate, to continue looking in deeper. He looks at layer 3. He sees that the destination address is 10.5.1.1. And the router says to himself, oh, that's not my address, but instead of just discarding it, because I am a router and because I know how to get to the 10.5.1 network, what this router will do is he will re-encapsulate it and forward it to this next router. So as we take, this is router 1, this is router 1 and router 2. So as router 2 gets it, the bits are being forwarded over to router 2. So at layer 1 he looks at the bits. After he reassembles those bits into frames, he sees that, oh, it's destined for his layer 2 address because router 1 forwarded it to router 2's layer 2 address. Router 2 says, oh, it's for me. This layer 2 address is for me. He continues to decapsulate, looks at layer 3 and says, oh, the destination is not my IP address, but I am directly connected to the 10.5.1 network. I live on that street. So what he will do, router 2, is he will go ahead and re-encapsulate it and put on the correct layer 2 address for the server. And he'll send it out this interface. So we're almost there. So then what's going to happen? Let's say this is switch 2 and this is switch 1. So now switch 2 gets it. And switch 2 receives the bits, looks at the frames at layer 2. It says, oh, I know exactly what the layer 2 address is of this server, and then the switch forwards it out the correct port. So we go up the protocol stack up to layer 2 and back down on switch 2, and then finally we're at the server. So this is server, we'll call it server 2. So server 2, he receives the bits at layer 1. He looks at the frames and says, oh my goodness, this is addressed to me. So he continues to de-encapsulate. See, what happens is somebody receives a frame and they are not interested in it, meaning it's not their MAC address and has no relevance to them. They won't continue to de-encapsulate the data. They'll simply throw it away because it's a waste of time. But because it's destined to the layer 2 address of the server, he'll continue to look at it. He looks at layer 3. It says, oh my goodness, this is destined to 10.5.1.1. That's me. So what does he do? Here's the key. If it's interesting to the device you're sending it to, if it's directed to that person or to that entity, it will continue to de-encapsulate. So it looks at layer 4. And it looks at layer 4 and it looks at the destination port information. So way back here, the application layer up here, when it started to create the session, it said, I want to send this to destination port 80, which by the way is a well-known port for web traffic. And because our server is a web server, guess what? It's listening on port 80. So it has a service running at the application layer that's basically listening to requests on port 80, and the request makes it in, and the software on that server processes the request. You know what happens next? There's going to be a reply, and it's going to go all the way back through the same flow. So the server would encapsulate the reply traffic down all the layers of the protocol stack. In this case, it's TCP/IP. It would forward it to the switch, who would look at it at layer 2, make a forwarding decision, and R2 would receive it, look at the layer 3 address, re-encapsulate, make a forwarding decision to router 1, who would look at it, make a re-encapsulation, send it to the switch, who would basically forward it to the PC, and the PC would get it. So that's a lot. But what I'm going to do is we're going to leverage everything we learn together, and we're going to apply it and move it forward. So this has been a great review of how the OSI reference model works. It's also been a really good practical application to see it in motion. Also, the graphics I've used here, this is the graphical representation for a router, and this is the physical representation of a router. Most of the time you'll see one or the other. Usually you'll see the icon and not the actual physical, but I wanted to show you physically what they look like as well. So on layer 3, we have our IPv4 and IPv6 addresses. IPv4 are shorter, IPv6 are longer. We also took a look at the EUI64. The router is considered a layer 3 device. Why? It's considered a layer 3 device because it makes forwarding decisions. Check this out. It makes forwarding decisions based on layer 3 addresses. And that's also why a switch is called a layer 2 device, because it makes forwarding decisions based on layer 2 addresses. So if you have a device that's primarily making forwarding decisions based on a certain layer of the OSI reference model, it could be considered that layer as far as where it primarily operates. Hubs at layer 1, switches and bridges at layer 2, routers at layer 3, and of course the header, once we add the header to the data at layer 3, the IP header, we can refer to that data as a packet. All right, there's a couple other terms that are out there that I want to kind of clear the air on, and one of those is a multi-layer switch. What exactly is that? Well, let's talk about that for a moment. A multi-layer switch. Well, here's what it means to me. I think, well, switch sounds like layer 2. And if we're not talking about anything else, just switch, that's where I'd go. A layer 2 device making forwarding based on MAC addresses, layer 2 addresses. However, if they say multi-layer switch, that implies that's a device that can make forwarding decisions at multiple layers. And that's exactly what that is. And it's been a big buzzword. A lot of sales have been made as a result of it. But a multi-layer switch is a device that can make forwarding decisions at layer 2, for example, which would make it like a switch. And it can also make forwarding decisions at layer 3, which would make it like a router. So what do you call a box? If we have a box like this that combine the functions of the switch and the router in one box, what would we call it? We call it a multi-layer switch. And usually a switch by itself is very, very fast. It makes its forwarding decisions by using dedicated hardware and circuits that are built into the switch. So a high-end switch is very, very fast and has the ability to move millions and millions and millions of frames very quickly. So if we had a single box that did all of its forwarding decisions for layer 2 and layer 3 in hardware, which makes it super fast, that would be another good example of what a multi-layer switch is all about. One other topic that comes up from time to time is the concept of encryption. So if you had to place encryption in the OSI reference model, where would you put it? And if we go back to the King A, King B, which is a really good idea, by the way, always go back to the foundation, to the basics. With King A, King B, the encryption happened at the presentation layer, layer 6 of the OSI reference model. Now, you and I both know that we don't use layer 6. We use the application layer in TCP/IP, which has layers 5, 6, and 7 all bundled into one. So encryption, without any other clues, very well could be a layer 6 function of the OSI reference model. But let me ask you a question. What if we built a device that took the data from this router, which are packets that it's forwarding, and we had it encrypt them on this segment? We make a special device that takes the packets right here, encrypts them, and sends them over here. That could be considered a layer 3 function. Why? Because we're taking packets all by themselves, encrypting them, shipping them across the wire, and having the other side decrypt those packets so that anybody who tries to steal the data right here wouldn't be able to make sense of it because they couldn't decrypt it. So with encryption, there can be layer 2 encryption, layer 3 encryption, and you can also have application layer encryption. There's also layer 4 encryption. Lots of variants. So the encryption function doesn't fit cleanly into any one category as far as the OSI reference model, but I'll tell you what does fit very cleanly. It's these guys right here. And these are the ones I'd take home and make sure that you've committed to. Layer 1 network interface cards, cables and connectors, also airwaves if you're using wireless, a hub, and the currency there is bits. At layer 2 of the OSI reference model, which is the data link layer, we've got layer 2 addresses, MAC addresses on Ethernet networks. The network interface card could be considered a layer 2 device as well. Why? Because it does indeed have and own that layer 2 address that's burned in from the factory. Switches and bridges operate virtually identical, except switches have more ports and more buffers, and bridges are more old school. And the currency, the actual PDUs at layer 2 are frames. And then layer 3, we have street names and house numbers, IP addresses. Whether it's IPv4 or IPv6, it's the same exact concept. And a router, primarily making forwarding decisions at layer 3, is considered a layer 3 device. And the currency, the PDUs at layer 3, we simply call packets. I have had a lot of fun walking you through this and discussing it with you. I hope this has been informative for you, and I'd like to thank you for viewing.